Thank you very much, Dr. Shastri and ISA, for giving me an opportunity to make a presentation here. In my presentation, I have divided this into, basically I'll talk about industrial R&D and bit of lab R&D also, and try to go to specific cases if time permits. Okay. So now, looking at we all know that solar cells are of three types, three generations rather. Mono and multicrystalline silicon solar cells, that's first generation. Second is amorphous CAD telluride and copper indium gallium selenide. And third generation belongs to organic dye-sensitized and perovskite family of solar cells. This is the way the shipment grew over the years. 2016 figures were somewhere around 75 gigawatts, and 2017 figures are estimated to have just touched 100 gigawatts. Now here, as you can see, thin films occupy about very little, about 6%. Next slide has the numbers actually. Mostly it is mono and multicrystalline silicon. And it's going to stay here for a number of years together, more. Here we can see how what is the shape, share of technologies of the shipments. We can see thin film has got 4.9 gigawatts out of the total kitty, and which makes about 6%. Multicrystalline silicon about 70%, and monocrystalline silicon 20%. Now mono is going up a bit more because N-type silicon is making an entry, and it stands at about 40% today. Now, this slide, now here I start looking at the industry, what is the strengths in industry as projections are made. We can see that multicrystalline silicon hyperpure type that continues for most of this thing, and then mono is gradually taken over, and mono N type, this is mono P type, and then mono N type also making a big contribution later on. In 2020-28 is going to be mostly mono, 40-60, that is going to be the distribution. Now coming to, because we all know that silicon wafers are cut from ingots. Now in ingot cutting, different technology has come in. That's diamond wear saw based cutting. That makes, for mono it's almost total. For multi, it's gradually making this thing. Can I show here? Yeah. Can I show the pointer here? Pointer. Yeah. So for multi, this is gradually diamond wear saw is taking over. The difficulty is in mono, because we all know that wafers have to be textured. They have to be, surface has to be made undulated, because to enhance trapping of solar radiation. This happens very easily in diamond wear sawed monocrystalline, but does not happen very easily for multicrystalline silicon. That is why it's taking a little bit more time. But finally, people hope that it will be all diamond wear saw, multicrystalline silicon also. Now texturing of multicrystalline silicon is an issue here. So people are trying alternate method like acid texturing is the most common, but now people are going for metal assisted chemical etching. That is gradually taking over, and finally little bit is our reactive ion etching based this thing also is going to come up later on. After the wafers are prepared for the surface texture, next one has to prepare a junction, and here the key figure is the sheet resistance, how deep you make the junction. We cannot afford to make the junction very deep because there will be loss of carriers in that case. So we are at 100 ohms per square of the sheet resistance, the top layer, but it's going to go to 138 ohms per square. Along with that, we are going to improve the technology of silver paste also, so that it's able to make proper contact to this very shallow junction without puncturing it. Diffusion is going to remain at gas phase POCl3 based diffusion mostly, without much changes. For metallization, we have in front side metallization is going to be mostly screen printing. It will remain the mainstream. Stencil printing may be slightly much later on, but basically it will be screen printing only. On backside technologies, you have screen printing totally. I mean, very little of plating will come on much later. The finger widths are going to go thinner and thinner. From 45 micrometer today is going to go to 22 micrometer later on, just reduce the coverage. So busbar will gradually increase from 3 busbars to 5 busbars and sometimes 6 busbars also. So busbars is 3 to 4 to 5 to 6 plus, like that is going. And finally, people are contemplating to have busbar-less solar cells also. Technology of printing, single print is going to dominate. Double print, print on print may come up later on. Dual print also may have some share. Dual print means fingers and busbars, they are done in 2 different strokes. Rear side passivation, because this passivation of rear side is becoming very important in order to reduce the loss of carriers. So here PCVD aluminum oxide is going to be the mainstay for PERC solar cells. Finally, the technology share of the cells as we go through the years is going to change, because right now is aluminum BSF is controlling the main market share, but this PES, the passivated emitter rear cell configuration, is going to take over gradually and finally occupy the major share in the market. Along with that, we will have heterojunctions. Heterojunction means non-diffusion based solar cell, like you have heat solar cell, heterojunction solar cells, and many other versions are coming. Carrier selective contacts based solar cells are also coming in. They also are going to develop and occupy a little bit. And then IBC, interdigitated back contact. Here what happens, both the contacts are on the back side, both top and, I mean, positive negative contacts there on the back side, to leaving the front absolutely clean and thereby gaining in current. And a little bit of development is going to take place here in silicon tandem. That silicon is going to, like perovskite and crystalline silicon, they are going to be probably put together and efficiency try to increase. Here, as these are efficiency projections. In 2017, for example, for BSF cells, we are at certain values. This is going to go up to 20%. It may go, but we are going to shift from BSF based to PERC based cells. So PERC is here. PERC is going up much faster than that. So this brings us to an end of the industry based technologies. Now we switch over to lab-based technologies. This is the very popular this chart from NRL, which every month they chart or improve or modify this efficiency. They track all the different efficiencies as they keep on improving. So here we'll go to figures later on. Okay. Here, this is also a very standard chart prepared by solar cell efficient Martin Green from University of New South Wales and his associates for showing us where we are today. For example, crystalline silicon solar cells, we are at 26.7% efficiency, and that also this area, every details is given technology. Silicon is here, then we have thin film calculated CIGS, CDT, CZTS is here. CIGS, for example, is 21.7% efficiency, although in small area. Module we'll see later on. Then amorphous, of course, although this is obsolete technology, but efficiency figures are very. Perovskite is a very interesting case. Perovskite has made a very rapid improvement in technology efficiency from 2009 to 18. It has gone from 3% to 22%. This figure is improved to 22% now. Perovskite, then dye sensitized and organic, all the data are here today.
But this is the lab results, right?
These are lab. These are the lab. Because industry already.
In the market, what is the highest efficiency available?
Market monocrystalline is available about 19 to 20%. Yeah, PERC cell about 21, 20, slightly more than 21% are available. PERC cells. Okay, this shows now tandem junction, multi-junction. That means here perovskite and silicon are put together, one on top of the other, and efficiency has gone up. Amorphous silicon, of course, although we need not talk about right now. This shows the module. What happens to the module? These are champion modules, not the what is available in the market. But silicon crystalline modules, they're available at 24.4%, multicrystalline 19, about 20%, like this, all the technologies are covered as far as modules are concerned. So from cells to modules, there is loss in efficiency. This is just for records from Fraunhofer, this thing. What we have just seen is summarized here. You can skip this. Now here it shows what is the difference between module and cell. For example, mono cell and mono module. You can see the difference, 26.7 to 24.4. Multi-silicon, this cell and this module. Like that, all the technologies, when they go from cell to module, there is a loss in efficiency, which is but natural. We can go to some specific cases now. For example, this is the configuration of the standard aluminum BSF-based solar cell, which are ruling the market today, aluminum BSF-based. From there, people have gone to PERC cells. PERC means, that means on the back side, you can see the entire aluminum paste, this back surface field is only localized. Rest of the silicon is virgin. That improves the performance of the cell, as the shipment details have shown earlier. Now this also has two, one is monofacial, that means light is coming only from top and producing, generating electricity. You can have bifacial also, that means on the back side, instead of covering the entire back side with aluminum, you can have gaps in between, cover with aluminum only where the doping is done. So light can enter from here also and generate current. You can see here, like bifacial cell, front and back, they almost look the same. Whereas monofacial cells, front and back, they do not look the same. So in bifacial cells are going to be important later on, because they are also going to have some contribution in the shipment ultimately, because it's going to have some advantage. So Longi China has recently announced an efficiency of 23% on bifacial PERC solar cell. We record bifacial at over 82%. Now, both PERC, mono and multi, there's a problem of degradation. Light-induced degradation and light enhanced elevated temperature induced degradation. Both the types of degradation are prevalent for mono and multi. Now this has been tackled, this LID problem in mono has been tackled in some way with hydrogen treatment of PERC cells under light and elevated temperature. But for multi, the solution is yet to be found, although people are trying everywhere. This is another type, the heterojunction solar cell. So far we have been talking mostly about crystalline silicon diffuse junction based. Now this is heterojunction, where there is no diffusion involved. It's just only deposition of some few layers. On a crystalline silicon solar cells, you deposit amorphous silicon P and intrinsic amorphous silicon layer, very thin layers. So cover it to IDO and put your grid here. This is screen printed grid, both sides, and your cell is ready. So this also is in manufacturing by Sanyo. Sanyo has been the only company who has been able to put in manufacturing. Very little this thing is there, shipment portion is there, this thing. But this is also available, possible to figure it out in a bifacial configuration. I'll just show in the next slide. But here I show a Kaneka in Japan that has produced the highest efficiency of crystalline silicon solar cell using bifacial hit solar cell as 26.6%, whereas Panasonic has produced about 25.8% using monofacial PERC, monofacial hit. Here, this is the configuration of bifacial heterojunction solar cell. You can see both all the contacts are on the backside, front is totally clean. So this is how they have got 26%. This is another way of making high efficiency solar cells. This is called sun power technology of this thing. Both the contacts on the back side. You can see this is N-type silicon solar cell. Sometimes they take P-type also with high magnetic lifetime. They put P and N junction, both the contacts together, and this is called IBC, interdigitated back contact solar cells. SunPower has been doing it for years together. They already have manufactured this, commercialized this technology. Yes. Yeah. Okay. So like this, okay, we can go to this another very interesting concept in solar IBC solar cells. Polo, it's called Polo. 26% solar cells have been produced using this technology. This is coming to CIGS. CIGS is making still some noise. They are going to 18.72% aperture efficiency has been produced by CIGS. This is a structure. And Solar Frontier has produced 23% conversion efficiency, about 1 centimeter square. The last but not least, this is perovskite solar cell, which has made very interesting progress from 2009 to from 3.8% to 22.7% in 2007. It has come up. It has got many disadvantages, but very big promise. So people are working on this. Probably one day this will be commercialized and make solar cells really cheap. Skip this? Okay, thank you very much.
Good. Thank you.